Welcome to this lecture on field programmable gate arrays and the course Digital System Design with PLDs and FPGAs. Last lecture we have started with the field programmable gate arrays. At that point we kind of contrasted the FPGA architecture over the CPLD. Essentially we told the CPLD has a kind of a central interconnecting switch between the logic blocks, but in FPGA the switch is distributed, so the whole architecture is scalable. And second feature of CPLD was very wide product terms, which is not required in practice, that wastes a lot of area. So in FPGA you have kind of lesser number of inputs to the combination circuit. So essentially that is these two allow the FPGA to scale to larger quite a complex size, and we have seen the evolution of FPGA from ASIC to the standard cell to the field programmable gate array. What is, in a nutshell, what is the architecture of the FPGA, a general architecture of FPGA, and we have discussed the programming the technologies. That means basically how this configuration technology, what are the different type of configuration technology, and we have seen some commercial chips, commercial devices from the major vendors. Okay, maybe those are the only vendors as far as FPGAs are concerned. So today we will choose a specific FPGA, the Xilinx FPGA, and look detail into its architecture, and which will basically enable you to tackle, understand even the much more complex FPGAs from Xilinx itself as well as from other manufacturers, because most of the people use somewhat I would say somewhat similar architecture. Unlike CPLD there are variations, but I would highlight that variation, showing some examples wherever there is a kind of drastic architecture variation. Okay, so quickly we will have a look at the last lecture's slides, then we will get on with today's lecture. So let us move on to the slide. So we looked at the evolution kind of from a very low level design to using higher level blocks and interconnecting, and the interconnection made at in the foundry. But in FPGA the interconnection is with programmability is built into the gate, this array of logic resources, so that it can be programmed or configured in the field. So the game is between the NRE cost, which is very high for ASIC, medium for this and low for this. So this ASIC work out for huge volumes, and this for middle volume, and this for low volume, and the design turnaround time is very high for it and low for it. This may run into years and this could run into weeks depending on the complexity. Okay, apart from that, then one should not kind of go overboard. We definitely this FPGA has disadvantages, and it can be quite a complex. FPGA can be quite big and can be costly, and one cannot assume the FPGA appearing in kind of mass produced item like cell phones and all that. But nevertheless there is a definite role of FPGA in every digital chip design, because almost all the chips are kind of implemented first in a field programmable gate array, then moves to ASIC, almost all of them. Okay, and the FPGA, as I said, has an array of, okay, though the name suggests array of gates, but that is not true. Its array of logic resources, it is a higher level logic resource which is used to build combination circuit with programmable interconnection. And when we say logic resources, we know that we have to implement data path, we have to implement controllers. So it has combination circuit and flip flops. When it comes to combination circuit, most of the FPGAs use lookup table as a combinational circuit element, and some uses multiplexers, some uses gates, and mainly I would say these are the Actel and diffuse FPGAs which uses the multiplexers or gates. And the programmable interconnection technologies are called SRAM, an unfortunate name, flash and diffuse. There are special resources like phase lock loop, delay lock loop, RAMs, FIFOs and memory controllers, network interfaces, processors, and these are many times depending on the requirement is is part of the silicon. Okay, this is a hard coded devices which I am talking about. Okay, so that is field programmable gate array in nutshell. We have seen commercial FPGA, Spartan and Vertex from Xilinx, and Cyclone and Stratix and Aria from Altera, and Actel has this Pro ASIC Plus and accelerator and radiation tolerant version of the accelerator, Smart Fusion with ARM core and things like that. And of course as I said, the Xilinx has a sync with dual core ARM, and the Altera has soft core Neos processor. So this is the general structure of an FPGA. IO pins around, array of logic blocks. Normally this will run into tens and hundreds, okay, like across and across the row and across the column. Okay, so this may be typical numbers will be for small one 50 by 50 to maybe 100 by 100. It may go all the way to huge numbers. Okay, and that shows that you cannot interconnect those blocks with a single switch. So there are wires laid out in a regular pattern, like at the junctions are the switches and the wires run. So and these left and the left and the bottom are the input to the logic block from these wires, and the top and the right are the output. And this is a very general, I am not talking about a specific FPGA, but maybe that when you take a specific FPGA, the input is from the bottom and the output is from the right hand side. And I have not verified the chip layout. It may not be available in the data sheet whether exactly these are kind of schematic. When you look very exactly, it may not look exactly like that, very precisely in this fashion, but nevertheless it resembles the implemented architecture. So you can imagine there are output coming, there is a switch here where the output wires are connected to any of the wires here, and you have a big switch here which allows the interconnection of these vertical bottom part or horizontal part, left right and things like that. So these are switches, all junctions are switches which allows connection. So when the tool puts some hardware into FPGA, it will be placed across multiple logic blocks, and depending on the circuit synthesize, that will be interconnected using these general wires. There are wires which span a single logic block, there are wires which span maybe 2 logic blocks, 4 logic blocks, 6 and the one end to the other. Okay, now these come from the statistics. It depends on what is inside a logic block and how many need to be interconnected, how close for a normal circuit, like on an average it might be that you take a 4 by 4 kind of matrix, the mostly the connections interconnections fall in here, then some are like you take this boundary, then it on an average it goes all the way up to the 4th or 6th, then such kind of wires are useful. And as I said, like when you interconnect, there will be a lot of switches programmed on the way, so the interconnect delay in FPGA could be quite high compared to a CPLD, but the advantage of FPGA is the complexity itself. A complex circuit can be implemented, and this shows a very detailed diagram where these are the switch block with horizontal and vertical wires. So this wire could be connected here, here or here, and you can program all that, and similarly output can be connected to any of the wires. There are 5 input going to the logic block, and that can be connected to any of these wires. So there are a lot of programmability, and this is called configurable logic block because the logic block itself is quite big. We will discuss why it is big. So it needs a lot of configuration. Okay, so that is it, and this shows a switch diagram like a horizontal wire, vertical wire is connected to horizontal, this wire and this wire. So at least one wire is connected to left, right and bottom, and that this shows various different types of connection depending on the statistics which each vendors use, different type of connections. Maybe we need not be seriously worried because our aim is to understand the FPGA and use it in our design than design the FPGA. So I will skip that, and this shows a diagram which from the Xilinx data sheet, which is very old, but this kind of highlight a thing which we should not forget. There are logic blocks which consists of combination circuit and the flip flops. There are interconnect wires, but underlying is a configuration circuitry to configure all these, and so you shouldn't forget about that. There is a lot of configuration overhead in terms of addressing these switches and programming it on, off and all that. So that makes compared to an normal ASIC, this makes the FPGA quite big. Maybe it dissipates more power, so the raw the speed of an FPGA may not be as high as say 1 gig or 2 gig. Maybe the serial transceivers go at high speed because that is easy to design, but a general lookup table speed may not be that high. So any reasonable circuit you place in route, it may not clock 1 gig, maybe 200 megahertz, 300 megahertz. Sometime if it is too complex, if you are not floor planning it properly, it might even go down sub 100. So but then it's not a processor, so you can it is up to the designer to exploit the available resources and do parallel computing, pipelining and so on, and kind of implement a very high throughput design to exploit this available resources. Okay, that's how with FPGA one achieve performances. So FPGA consists of IO blocks, and that has tri-state output and input, and it has a synchronizing flip flop because the input can come from another chip or another clock domain, and there are array of configurable logic blocks. There are horizontal vertical wires with programmable switches in between. These wires are single length, double length, quad, hex and long lines. It depends on, as I said, statistics of how spread is the circuit or the connections, and there are resources available to the user in terms of logic blocks, the memory, the PLLs and all that, and there are resources for configuring the programmable switches in the interconnect structures and logic blocks. Okay, we will see what is there to configure in a logic block, and this is where we have stopped. The programmable technologies are SRAM, flash and antifuse, and we said that the SRAM basically use a transistor, NMOS transistor, for interconnecting the two wires, but then if the gate is like if it is an NMOS transistor, if gate is 1 it makes a connection, gate is 0 it cut off the connection. Okay. Now at the gate is a flip flop which holds that status of the connection. If the flip flop is set to 1 then it conducts, if it is 0 it does not conduct. So that means that these flip flops, all these are flip flops which need to be programmed at the power on, because at the power on there is no specific state. Now to program it, now like it's too much of an overhead to kind of independently address and program it. So you do not program it serially, you program it parallel. So this flip flops are organized as a static RAM of width 8 or 16 bit, and the vendor knows the kind of the position to decide on the format of the configuration file, and that is why it is called SRAM. Okay. When you say the programming technology is SRAM, no way SRAM can interconnect something, but the pass transistor is the interconnect technology. The flip flops are used to store the status of the gate, and flip flops are organized as static RAM to ease of programming. So in the previous families of FPGAs it was 8 bit wide, and the current FPGAs use 16 bit wide programming, and that I am telling the kind of the raw internal structure, but then there is a way to program serially as far as the user is concerned. We will see that. Okay. So what one issue with the SRAM is that this is a single flip flop. Okay. So you look at this whole block. Okay. Now I hope you remember that this is a logic cell, this is a logic cell, these 4 are logic cell, and these are the horizontal wires, these are the vertical wires. So we are talking about interconnection at this big switches and output interconnecting to the vertical wire. Okay. Just an explanation on the diagram. Now we are looking at this, we are blowing it up, this one. So we have a right transistor, we have a kind of switch which is a transistor and a flip flop. Okay. So that is what is shown here. You have a switch, the gate of that is connected to a flip flop, which is nothing but in cross connected inverters. Okay. So and now you have to force this inverter to 1 or 0. So this is a right transistor, suppose you want to force this to 0, then what you do is that you put a 1 here, enable the right transistor, this is forced to 1. So 1 this becomes 0 and 0 comes here, it is latched and that can be removed. That means you give a 1, you give a pulse here, then it gets latched onto the flip flop, and the pass transistor is on or off depending on what you give here. Okay. Only thing is that you give the opposite of what you want as far as the structure is concerned. Important thing to remember is that the flip flop are made of 2 inverters, and one inverter is made of 2 transistors, one NMOS and one PMOS, PMOS to the VDD, NMOS to the ground. So that this inverter is composed of 2 transistors, this 2 and this one is the 2 plus 2 5 and 6, and this can be sometime a right transistor with isolation can be big. So one switch means 6 transistors. Okay. So you can imagine it occupies quite a lot of area. So if you assume, say here it is shown 7 wires. So if it is a 7 into 4 28 wires, even if one wire is connected to 3, you can say 28 C2 kind of connections are available for it to connect to everything else. So it's a quite a 28 into 27 by 2 connections may be there. So that involves a lot of transistors into 6. So these switches occupies quite a lot of area. So that is one kind of disadvantage of the SRAM kind of technology, that the switches occupy a lot of area, and of course there is a delay because once you there is a delay of the channel. Okay, so it introduces, each switch introduces a certain delay. So when you cascade multiple switches from source to destination, it adds to the delay and it occupies a lot of area. And these, as I said, this whole thing is organized as SRAM cells, of certain width, hence it is called the static RAM technology. And when it comes to MOS transistor, we have seen that with respect to the PLDs, CPLDs, and MOS transistor has it's a normal MOS transistor with a floating gate. It conducts when it is not programmed off, and it can be electrically programmed off or on. We have seen the kind of basic working of it. So you have an N channel transistor, NMOS transistor with N source, N drain, P substrate. You have silicon oxide, a polysilicon gate, then again silicon oxide, the controlling gate. Now normal case you apply the positive voltage, channel forms and conducts, but the trick is to trap some electrons here to make the threshold voltage quite high. So if you apply normal threshold voltage, because electrons are sitting here and kind of you need a higher field to form the channel. Okay, so that makes it off. Even if you apply the control gate with a logic high, it doesn't conduct. So that is how it is turned off. So that is shown here. The source is grounded, drain is given the supply voltage, a pulse is applied, a higher voltage pulse is applied. So electron tunnels and get in here, and then the normal application of the gate voltage wouldn't make the channel and it wouldn't conduct. And when you want to erase it, you do the opposite, you ground it, the gate you ground, you apply a pulse here, it gets out. So one advantage of the flash is that it can be programmed on or off electrically, and much more than that, if the chip has a port for doing that within the circuit, you can program it. So somebody makes an FPGA or a CPLD with that technology on the board, at the destination, it can be kind of, and it can be updated. And nowadays more and more kind of over the network update, or sometimes it's called over the air update through the wireless channel, the firmware is updated, and maybe even the hardware many times can be the updated. Like if you have a programmable hardware, not only the flash memories, the programmable hardware also can be updated remotely through the network, wireless and all that. So these technologies enable that. And the third one is called anti-fuse or anti-fuse, and you know that in a chip design you have layers which implements the transistor, and you have layers with interconnecting wires. Okay, so you cannot have the wires in the same layer as the transistor, so they are on a different layer, and the layer to layer connection is by drilling a hole, and normally on one layer the wires will run horizontal, in the next layer the wires will run vertically. Okay, because it's easy to interconnect, also the kind of the coupling between the two tracks will be less, the capacitance between the tracks will be less. So essentially if this is assumed that this is a horizontal wire, this is a vertical wire, normally they'll at the cross point there will be a hole drill, and that will be conducting, it is made conducting. Okay, so in an anti-fuse FPGAs the connection is made through this hole. Initially the hole won't be conducting, there will be a fuse material, a special fuse material deposited, it shows a cross section of that, and normally it is not conducting. This shows the kind of the horizontal wire on the top layer, and this shows a vertical wire which is kind of coming out of the screen towards you. So there is a kind of hole with a proper deposit, and you apply a high voltage. When I say high voltage, like a kind of nearing 10 volt, and then it fuses and make a connection. Okay, which is permanent, which cannot be kind of erased. Okay, so that has certain advantage. So it doesn't kind of a noise wouldn't reverse the status of connection once it is programmed. So these kind of technologies are used in the space application mostly, so that anything sent to outer space is exposed to a lot of radiation, and this can kind of flips the flip-flops, and that can cause problems. So the antifuse is used, and it is not very kind of little bit you say resistant to the reverse engineering. If somebody try to kind of peel the chip and take the photograph of the mask, then one cannot make out the hole is kind of programmed on or off. So that is an additional protection from kind of piracy, the hardware piracy as far as this is concerned. But in SRAM kind of FPGAs, you know that the status of these flip flops has to be stored somewhere, and at the power on it has to be programmed, and if somebody can read those memories then this design can be pirated. But nowadays there are encryption technologies which is available to protect the configuration file which is stored in a memory, okay. But this has an additional advantage of that the summary is shown here. So in a flash kind of technology, it's non-volatile. Once you program it till you erase it, it retains. It's good that way. It is reprogrammable in circuit, and the delay is quite large, area is medium. But when it comes to SRAM, it is volatile, that means at the power on it has to be reprogrammed. But then you know that the flash has some kind of limitation on the number of times you can program. It is not that it kind of it's a serious limitation as far as FPGA is concerned. Is not that when you design with FPGA you program it 1000 times a day because it takes time to design, and the designers do a lot of simulation and verify everything before going to the chip to program the chip. But still that SRAM has no such great limitation, that number of times it can be programmed. So this is very good for prototyping, and particularly I would say coming from academic institution, it's very good to give it to the students, you know. They can program, reprogram, and it runs for quite a long, you know, you can use it for 3 years, 4 years without trouble. So this is also in circuit reprogrammable. Delay is large, area is large, we have seen the large area. When you say antifuse, it is non-volatile, it's a one time, it is not reprogrammable. But you see the delay is small because it is not through a you know active circuit like transistor, it's a connection, it's a fuse connection, and the area is no extra area like there anyway the interconnection of the wires require the vias, which is called vias or vias, so the hole, and so this deposit is in that vias, okay. So there is no additional area, but definitely to apply the voltage you need a transistor to isolate that voltage. So definitely there has to be right transistors at that place, but still it does not occupy much area. Now this has some effect, this programming technology has some effect on the size of the logic block, okay. So this is one important thing, though nowadays most the complex FPGAs are SRAM. So this is kind of forgotten, but then one should realize that when you take say an anti-fuse based FPGA, since the area of the interconnection is very less, they are able to make the logic block small, okay. So this is something to do with the kind of fragmentation like you would have seen in a hard disk. Say there are sectors, okay. Nowadays you have you know the terabytes or gigabytes of you know the space on the hard disk, but there are basic units, you know, it's not that the hard disk can accommodate byte wide storage, it is a sector wide storage, and earlier the sectors were 512 bytes, but now it is kind of 4K, 8K depending on the size of the total size of the hard disk. Now advantage of choosing small size is that less space is wasted. Suppose the sector size is a 4K, okay. Suppose on an average the files have less than 4K size, okay. Suppose 60% of the files stored in a hard disk is less than 4K, then a lot of area is wasted. So there we can say there is fragmentation or unused area in each sector. So choosing the size of the sector depends on the average size of the file. So it will be ideal if we can choose it very small enough so that nothing is wasted, you know. Like if it is make 512 bytes, the maximum waste will be 512 bytes. Maybe if there is a file which is very small, so only 512 is wasted, but then in the case of in 4K, the 4K can be wasted, you know, for a very small file, or there is a file which is just little above the 4K, so that that might affect. So that I am talking about the fragmentation. Same argument, I was coming back to the slide, same argument applies here. You know, in a fine grain the fragmentation will be less, but that is possible because the interconnection area is small. But when you use an FPGA with SRAM which occupies lot of area, if you make the logic block very small to avoid the kind of wastage within the logic block, then the switches will be much bigger than the logic block, okay. So what this kind of FPGA vendor do is that they make the logic block quite big because interconnection is costly. So they make sure that quite a lot of things are packed into the FPGA, but then there is a great danger that only part of it is used. So the this kind of FPGA, which is called coarse grain FPGA, and the second type is called fine grain. The coarse grain FPGA, the vendors make sure that the logic blocks are very flexible. That means that they make sure that everything can be used. Suppose you are using a part of a logic block, other part can be used. Say we have seen the CPLD. In a CPLD, the and OR section output goes to a flip flop, okay, or in a PLD like 22V10. So you can bypass the flip flop, there is no problem, okay. So but if you bypass the flip flop, that flip flop cannot be used separately, okay. So that is a waste, okay. But we will soon see that in an FPGA the FPGA vendors make sure that, like if the combinational logic alone is used in a particular logic block, the flip flop can be separately used for something else, you know. These kind of things are available. That is how they exploit the kind of disadvantage of the large size of the static RAM, and most I can say they are successful in doing that. They are not bogged down by that. So though there is a division, there is no great disadvantage with the coarse grain kind of architecture, okay. That is what I want to highlight. I will just show a picture. This is a coarse grain FPGA, basically a Xilinx FPGA. You can see that it is a logic block, configurable logic block. There are two identical slices and they call it slice, and within a slice there are identical blocks, two blocks, and there is a lookup table, 4 input and flip flops. So a logic block has 4 lookup table and 4 flip flop, okay. So and this lookup table itself is 4 input, which allows you to implement 4 input variable implementation. So it's quite this is quite huge, okay. It's coarse grain, and we will see this in detail later. And if you take, this is a taken from a Actel FPGA, Actel 54X, okay. I should have shown that. So this is taken from the Actel data sheet, the 54X FPGA. So you see the essential combination circuit is a 4-to-1 multiplexer, okay. You know that the multiplexer is nothing but AND OR circuit, and if you want to implement a Boolean function, it is possible, say you connect a variable A here, B here, then this line represent A bar B bar, AB bar, A bar B, sorry A bar B, AB bar, and AB. Okay. So depending on, like, you want to have an AB bar or A bar B, say you choose 0 1 1 0, then you get that implementation. So this is how, it's a very simple, 2 variable, but in this case there is an AND gate with 2 inputs, OR gate with 2 inputs. So normally if you want 2, then you connect 1 to the logic 1, other uses variable, but in some cases like you give A, B, C, D, then some combination of product terms of 5 variables are possible. And you also remember that if you connect an A, B, and instead of giving 1 0 here, if you connect a third variable here like C, C bar and so on, you could make 3 variable implementation. So with this, like 1 variable here and 4 here, maybe some combination of 5 variable can be implemented, otherwise 3 variable implementation can be done. So that's a fine grained logic cell of an FPGA. So design methodology, we have discussed this during the VHDL lecture, but then if you have not gone through that lecture for some reason, you are looking at the FPGA part of the lectures, then we will just illustrate that. So the design methodology is currently you start with a hardware description language like VHDL or Verilog. You describe your circuit in VHDL or Verilog. After that you simulate that. It's called functional simulation. Sometimes people call it behavioral simulation. These are just names. Sometimes people say the behavioral simulation is nothing but functional simulation plus the timing details, but nevertheless I mean by functional simulation the basic code is simulated. Okay. Now that's not the circuit you are simulating. When you say Y is assigned A and B, we are not simulating the AND gate, we are just simulating that AND function. Okay. So there is no circuit here, this is the basic source code. It's very fast because if you make syntax errors, you make logical errors, that can be quickly corrected at this point before generating the circuit. So that is that functional simulation. Then you go to a step called synthesis, okay, wherein this the source code you have written is synthesized into a netlist of logic gates and flip flops. Maybe it's Boolean equation in the case of the combination circuit, but it is the logic circuit is generated out of your description. Now if you are a novice, if the designer is a novice, he or she can go for a logic simulation. That is different from this functional simulation because here we are simulating the logic which is generated by the synthesis tool. Here you are simulating the code you are written, the code in human readable English, that syntax is simulated here, but here the logic is simulated. But mind you, at this point or here there are no delays because it's not yet implemented in a device, so there is no delay at this point. So you give to an AND gate A and B at 10 nanosecond, the Y which is the output come out at the 10 nanosecond. Okay. So no logic delay or interconnect delay, so there is no delay here. But mind you, here you are simulating the code, here you are simulating the circuit without delay, and maybe you can, if you simulate that, if you find errors, if there is synthesis errors, then you can go back and iterate. So you iterate here, you iterate here, but for an expert designer who knows coding, which I have taught you in the case of VHDL, knowing a particular circuit, how to write the proper VHDL code so that you get what you want, then in that case you really don't require this logic simulation. And then you go to a step called place and route. That is basically like going back to this diagram, maybe like you have maybe yes here the synthesis tool will generate a logic circuit. Now the FPGA has an array of logic blocks. Now that circuit, and these are identical arrays, and that circuit has to be placed in the logic block and has to be interconnected, and that is not a very easy task, because if you take one logic block, the first logic some circuit you have synthesized, a part of the circuit, like if there are kind of 10,000 or 100,000 logic block, you could place it anywhere without any constraint. If there is no constraint, the possibilities are too high. So the place that is the placing the circuit in a logic block and interconnecting it, okay, that's called routing. So that is what it says. So this is what the place and route, and at that point like the FPGA is a kind of general purpose circuit. The IO pins, your user input output signal can be assigned to any IO pin. So you can specify the IO constraints saying that you please map this particular signal to so and so pin, because maybe one advantage of FPGA is that even before designing the chip you can start with the PCB design, like you can assign the pin of the chip to a particular signal, and you can go ahead with the PCB design while you are designing the chip, okay. Ultimately some kind of a printed circuit board has to be used to mount this FPGA, so that can go parallel. So these IO pin assignment is specified in the constraint, and another thing which can be specified is that, as I said, the placement is a very critical thing to do, complex thing to do. Suppose you want some performance, you want to, like you designed a counter with the flip flops and next state logic, and you are planning to clock the counter at say 300 megahertz, then if the counter flip flops are kind of placed apart in the chip, like you maybe the chip, okay, the chip, we will come back to that chip diagram. Okay, here. So suppose a part of the counter is here, another part is here. So for the counter it has to be interconnected. So it may like it incurs lot of delay. It will be good if they are placed close together so that the interconnection wouldn't suffer a lot of delay, so that you will get a faster counter. So that kind of constraints called timing constraints can be specified at this point, which say that for a combination circuit from an input to a particular output, the delay should be less than certain time, like 5 nanosecond for 200 megahertz, or you can say from a register to through a combination circuit to the other register, which includes all the delay, TCQ, T combinational, T wire delay, T switch delay, and the setup time, everything. It should be less than 5 nanosecond. Then the place and route tool will make sure that the circuits concerned are placed together in close together, and the number of interconnecting switches are less, and so on, okay. So it can iterate over that. So it is, when you say constraint, you have the timing constraint, the IO constraint, all that is there. Then the place and route tool, which is called PAR tool, do the place and routing. Many a times in the case of PLDs it is called fitting, okay. So basically it's just a term used. You could in principle use the term place and route there also, but then you know that there is only there is no variation, there is no grade, there is a single switch between the logic blocks. So it is basically the how to fit the given circuit into the logic block is the main concern. So that is why it is called fitting. And once you do that, then at this point for the tool all the delays are done, all the combination circuit delay, all the wire delay, all the register delay, all the IO delay, everything is known. So a timing model is generated. Now you can simulate your synthesized and place and route circuit with time delays, and you give an input, the output come with a delay, so you do the timing simulation. So you should know that this are different. This is the original VHDL code you have written, you do the function simulation. This is the synthesized code which itself may be written in VHDL which is simulated. So the language may be VHDL but that is not the code you have written, and when it comes here still can be a VHDL code. Many times Verilog is used but with for certain reason for the timing model with the time delays this can be in the same language but totally different code. So that is timing simulated, but then it takes a long time. One thing to understand is that you give the input, then the simulator has to now calculate all the time delays which is composed of lot of individual time delay in between. It's not a gross time, so it's a time of the IO delay, interconnect delay, wire delays, and the lookup table, the combination circuit delay, various combination circuit components, everything had to delay. So there is quite a lot of the computation to do. So this can be very the timing simulation can be very time consuming. Okay, so for a complex circuit it might take a day to simulate that, and so at the beginning, like when you do the first iteration of the place and route, if you go for timing simulation and find you take 6 hours to simulate and find a small error, then come back and correct is a very hard thing to do. So there is something called timing analysis which is static timing analysis done. So this is dynamic in the sense that you give the input, you literally make the circuits work from the input to output. But here what is done is that this tool will look at the block delay, interconnect delay, and estimate the time from input to output for a combination circuit or for register to register for a data path or sequential circuit. Okay, but the problem is that there are no inputs. Okay, no inputs are specified, so the state machine or the controllers are not active. What is available is set of registers, combination circuit, set of registers, and it adds up all possible paths and show up the delay. Okay, now it may make mistake, it might report a path from a register to another register which is never used in the real circuit in real life. Okay, so because that the controller is the one which is controlling the data path, maybe there are 4 source registers, some combination circuit, and say 5 destination register. The real operation of the circuit only involve like a kind of one-to-one mapping. Maybe one register result goes to the other register, 4 of them, and maybe one of the register give the result to the 2 registers, sometime to one and sometime to other. But if you given to a static timing analysis tool, it doesn't know all that because it has no idea of the signal kind of signal status, okay, control signal status. So what it assumes is that 4 source, 5 destination, total possible paths are 20, but in real life is only 5, and it will report all the timing from source to destination of all the 20 paths. And you might, as a designer, you might find that 6 of them is violating the timing constraints you have put. Okay, but none of it may be used in the real life circuit, so you can be kind of misled in this game. So it's very important that when one do the static timing analysis, such information is given to the tool saying that what are the paths valid. Okay, like there could be another situation where there is a source register and destination register. The destination is not clocked kind of every clock, like the source get an input data but the result get latched after 2 clock cycle, but this that is enabled through the enable of the destination register through a state machine or a controller, which the timing analysis tool have no way to know. So it will assume that all the registers are working all the time upon every clock edge. So it will assume it will overestimate the critical path delay and there could be errors. So this has to be told to the timing analysis tool, then it will be very fast. So after the place and route, one do the static timing analysis. If that is not met, you iterate back now. Maybe you go back, change the constraint, you do certain change in the synthesis options, whatever is the correct option, or even go back and modify the circuit. And once everything is done, you do the timing simulation, again go back maybe this way up to here or up to here, iterate it. When everything is done, when the designer is satisfied, a configuration file is generated that you can program the chip. Okay. So that is what is in a typical tool. There can be more tools, more advanced tool, but at least bare minimum tools required for FPGA design is that you have a editor which can be internal or external, a synthesis tool, the place and route tool or a fitting tool, a programming tool, a constraint editor, a simulator which can do the functional simulation, logic simulation and timing simulation. Normally any simulator will do support all these three, and a static timing analysis tool. So, and many times the vendors give everything put together as a single kind of integrated design environment. So IDE, the Xilinx call it ICE, integrated system environment, or things like that, ISE. And sometime some of these tools, like there are vendors who give very good synthesis tool alone. Okay. And the vendors allow you to use that synthesis tool along with their the tool. Instead of, you can replace the synthesis tool which is supplied by the vendor and replace it with a third party synthesis tool and so on. But normally the place and route is done by the vendor, because the vendor knows the FPGA internal details, which is very much required for properly doing that. And many times it's not wise to give out this detail, because people can make out what is really inside, though we have the data sheet, but all the details are not exposed for keep the intellectual property. So that is the design methodology. And if you look at the commercial tool, just to give a flavor, and this is recording in 2014 January, I am not sure that after 2 years if you listen to this lecture, these tools will remain, or some companies, some vendors are given in the bracket that maybe one is acquired by somebody else. I have no guarantee, but as on now, as on 2014 January, you have the model sim simulator from Mentor Graphics, which is a very good simulator. Similarly, you have Active HTL simulator from Aldec. These are good simulator, but the vendors have their own simulators. And synthesis tool, you have Simplify Pro from Synopsys, very good synthesis tool, a precision synthesis from Mentor Graphics. But when it comes to vendors, the Xilinx ICE or ISE, it has everything. You have synthesis, simulation, power, programming, static timing analysis, constraint editor, power analysis, the floor planning, name it, everything is there. And these ICE tool work up to the chips of the family Spartan 6 and Vertex 6, but for Vertex 7 they have a different tool, much more kind of better tool called Xilinx Vivado, very good tool, a quantum leap in the whole tool technology. This is quite old, but this is quite new and good, but it is only now currently supporting the Vertex 7 series. Maybe as the years come by, this may disappear and this alone will be there. And Altera has Quartus 2, once again that has everything what you need. Whatever the Xilinx tools are there, everything is there. Actor Libero is again same, they have everything required for kind of for the FPGA design, their family of FPGAs. Now if you are a normal novice designer, you are starting with small kind of projects, then what you need is only this. But if you are doing very complex thing and you want very high performance, you want very high tight fitting, kind of reduction in power, you want the refinement in the area of the implementation, then you need to use these kind of things. And these vendor tools are improving, say compared to 5 years back. The current tools are really good, and you don't need to probably use the third party tool, but that is up to you to make a judgment. What you do is that you evaluate, like if you have if you feel that you are not getting the performance you want, you have done everything under the earth to get the performance, but you need a little more performance, then you can probably move from the vendor to a third party synthesis tool to get the performance out of it. So of course when coming to the other tools, we have the major VLSI designers, you have the Cadence, Synopsys, Mender. These are basically the synthesis tool and the simulator, very good simulator, but then you have to definitely do the place and route with the vendor tool. These also support. So maybe I think I thought of going further, but then it's good that a good introduction gives you a good grip on the subject. We will see the internal details of the Xilinx Vertex FPGA. I am taking that as an example. So what we have seen today is the programmable interconnect technology, SRAM, the flash and anti-fuse, a kind of features, what is the advantage, disadvantage, and we have seen how this forces a coarse grain and fine grain kind of architecture, and how the coarse grain people, the vendors, make sure that nothing is wasted. And we have looked at the design methodology, what are the steps, the tool flow in designing FPGAs. We have seen some commercial tool. Now I think I have touched upon all the introductory material to get a very good grip, and we will go detail into, we will take an architecture, Vertex architecture, which is not used at all, but it's a very good starting point. Once you understand that, any other complex FPGA architecture can be understood very nicely. So we will go into details, very much into details of the Vertex FPGA architecture. So please now on your part you can go through my slide, you can also read the data sheets of the vendor, the application notes from the vendor. There are a lot of material which is available. Maybe the textbook are not the ideal place to learn FPGA from. Don't waste your time on most of the textbook. I haven't frankly followed up, but then you can use a lot of the data sheets and so on. So we will see in the next lecture the details of the FPGA. I wish you all the best and thank you.